Hi everyone, welcome back. So this time we're going to be going over acceleration for polar coordinates. Now the instantaneous acceleration is defined as always as it's simply the time rate of change of our velocity. Now we know our velocity has multiple components, so we need to take the time derivative of both of them. If I do that, well, let's do one of these components together. So r dot ur, okay, r dot ur. So that would be d dt of r dot times u of r. And that would then be plus dur dt plus r dot. And that would be two components, so we can see here. So it'll be r double dot ur plus, and this one right here we already learned has a, it changes when we do it, so that would become, why did I do that as a plus sign? Sorry, that should be multiplication sign. And that would be r dot times theta dot u theta. So that one I have two components, and we'll go ahead and do this one as well. Actually, no, that was going to require some extra derivation, which I will let other people do right now. So, with that in mind, I'm going to erase this, but I'm just showing you that you're doing the chain rule again. We're just having to do the chain rule for this, and the chain rule for this, and erase all this. We can see what it comes out to be. And there we go. We get our full situation where we see that terms from both of these get added to both sides. So this term right here is the radial acceleration of AR. And this term right here is the transverse acceleration. Once again, along the radial or transverse directions. The magnitude of the acceleration is just the square of both components, add together, and then take the square root. That is all. Now, if you want a really good walkthrough of where all this came from, you can check your book. It will go through how, similar to how we had earlier, we can relate the time rate of change of our transverse direction to another quantity that we know. So check it out, see what you think. I'm sure you'll find it quite interesting. Or not, and you can just ignore it. Either way, these equations work. Okay, now cylindrical components. So probably been like, why are we in polar coordinates? I thought you said cylindrical coordinates. Well, we're here finally. It becomes cylindrical coordinates when we have a z direction. No longer just r and theta, but now z. So if the particle p moves along a space curve, its position can be written as this. Wondering, well, where's the theta in here? It's not really necessary, because r would include that. But, you know, we have our nice position. And its velocity can be shown like so, and its acceleration can also be shown like this. And if you look at it, the z component is extremely simple. We don't have any crazy derivatives for that one. It just stays, you know, position, velocity in the z, acceleration in the z direction. Just regular time derivatives. Very similar to how we had it in our Cartesian coordinate system. So we'll stop there for now, and then next time we'll move on to an example using these systems. I will say this, that for all examples and all problems using these equations, it's very important that you realize what you're given and also what that means. Like if theta dot is constant, well, it's not zero, unless it's constantly zero, but that means that theta double dot will be equal to zero. You know that from the problem statement if it gives you one of them. So be careful. Use what it gives you to help you out. So, thanks for listening. I'll see you all next time. Bye-bye.